Okay, in this first item we've got a two-span continuous beam. That means we have a full moment transfer. We've got a uniformly distributed load of the same magnitude on both spans, same span lengths, same EI, bending rigidity in each. We're asked to select which is the more correct of two proposed moment diagram shapes, explain why, and include any expected features of the moment diagram, such as estimated values at critical locations and inflection points, that sort of thing. Right? So what we note here is that because of symmetry, we know that we've got no rotation as a net result from the applied loading. And that means we can look at just one span here with fixed end in the middle, because that would give us that zero rotation. We got the prop out at the end, the roller end. Here's our uniformly distributed load. And we've done this one item a number of times. We have the fixed end moment table to tell us that in this, what we would in that table call a modified fixed end moment, that the moment that results here at this fixed end would be WL squared over 8. Notice we're no longer going to have to estimate anything here, because by symmetry we've reduced this down to an exact problem. We know that with the distributed load W being uniform, that when we integrate the shear integrate that to get to the shear diagram, we'll have a linear variation, and then to get to the moment diagram, we would of course end up with second order. So that would be at least one of the things that we want to go for. And yes, I did tip off which is the correct one. It's got to be B, because of the shear diagram here, right? That we have this constant, or rather linear variation of the shear, that we get a point load here at the support that's going to cause an instantaneous change in shear. It's going to go from a positive slope on one side, negative slope on the other, and really from left to right, negative slope to positive slope, not what we have here in A. So that's of course one big reason why A cannot be the correct answer. And we've done this a number of times as well. There's our moment diagram. So what's left to obtain are the values. We already know what's going to be the value here at the right hand side. That's a negative WL squared over 8. Right? So then it just comes down to, well, where's the inflection point and what's this maximum moment? Well, with the relationship of the shear and how that's all going to work, then we've got a 3/8 L there, a 5/8 L over on the other side. But because of that symmetry that's even there, I didn't draw that particularly really all that well. We're going to have 3/8 L and 3/8 L. That part has to be symmetric, right? That would get us that area balancing that area, and that would just leave us then let's see here, L over 2L over 8 or L over 4 to get us to the inflection point. So there's your inflection point location. And then our maximum, of course, we're going to start at 0 at the left, and we'll add in this 1/2 of 3/8 of WL times 3/8 L. So there's going to be a WL squared. We got 3 times 3, that's 9. We've got 64 here, and then you've got the 2 in there. So that maximum is going to be then 9WL squared over 128. So our estimate here, which might have been using this kind of system to get an estimate if our two spans were asymmetric, in this case, because they are symmetric, then all of these other numbers become exact, and our answer then of course is option B.